Welcome to today's Explainer. We're diving straight in today because we are unpacking something huge, a really fascinating shift in how our devices actually think. We're looking at Apple's AFM3 architecture, and more specifically, how a massive hardware crisis is being entirely solved by pure software genius. But to really appreciate the solution, you kind of have to feel the pain of the problem first. 83%. Just think about that for a second. That is the staggering spike in mobile DRAM prices in a single quarter, specifically Q2 of 2024. As these on-device AI models devour data like a monster, the memory required to run them is just setting smartphone profit margins on fire. Phone makers are facing this massive economic pressure. They literally cannot afford to keep infinitely adding expensive, high-speed RAM to your phone without completely destroying their bottom line. So picture the smartphone industry getting completely squeezed from three different sides right now. From one end, foundries are prioritizing ultra-high-margin server HBM for those massive cloud data centers. From another, you've got cloud providers hoarding enterprise SSDs. And then throw in geopolitical shifts, like China's CXMT expanding its market share, which is forcing localized supply chains. Mobile manufacturers are essentially caught in the crossfire of this massive memory land grab. The physical supply is shrinking at the exact moment on-device AI is demanding more of it than ever before. Here's our roadmap for today. We're going to hit the memory wall of mobile AI, explore a really helpful desk and library analogy, look at the fatal limit of NAND, uncover the software magic overcoming those limits, and finally, track the chain reaction this is causing in global supply. Part 1. The memory wall of mobile AI. Okay, so think about standard mobile chip architecture. You've got your DRAM, your high-speed memory. It's lightning fast, sure, but it's physically tiny and currently capped around 8 to 12 gigabytes on standard phones. Now contrast that with your NAND storage, holding hundreds of gigabytes, but moving at an absolute crawl. Next-generation AI models require tens of billions of parameters. They physically cannot fit into that tiny DRAM space. We have, quite literally, hit a memory wall. Part 2. The desk and library analogy. To really grasp how engineers are fixing this, let's use a simple mental model. Think of DRAM as your desk. It's lightning fast for real-time execution, but severely limited in space. It's where you do your active thinking. NAND, on the other hand, is your library. It offers massive space for deep storage, but it's relatively slow, taking time to walk over and grab a book. So, the crucial point here is this. If your desk is way too small for a massive AI model, the system has to learn to fetch exactly what it needs from the library, instantly, without trying to drag the entire library over to the desk. And that brings us directly into Apple's AFM3 architecture strategy. Instead of trying to awkwardly cram a massive 20 billion parameter model onto that tiny DRAM desk, they leave 100% of the model asleep in the massive NAND library. When you ask your phone a question, the system uses what's called a mixture of experts approach. It identifies and wakes up only the specific 1 to 4 billion parameters, the specific experts, needed for that exact prompt, and moves just those over to the desk. Part 3. The fatal limit of NAND. But here's the catch, and it's a dangerous one physically. NAND flash, it was never designed for continuous, high-speed, read-heavy AI workloads. Every single time traditional AI models generate a word or a token, they go back to the library to fetch new weights. This constant read and erase cycle causes something called read disturb. Basically, applying voltage to read one cell alters the threshold voltage of neighboring cells, causing physical degradation that will literally destroy the drive's lifespan. If you try to run AI this way, you'll just burn out your phone's storage. Part 4. Software magic overcoming limits. So how do we fix that? Well, when you look at standard routing, it's chaotic. It's constantly grabbing new data from the storage vault for every single token generated. It's slow, and as we just learned, it degrades the hardware. Now, compare that to Apple's instruction-following pruning, or IFP. It features one clean, one-way fetch. The IFP logic gate analyzes your entire prompt up front, figures out all the context needed, and fetches the data from the NAND's library into DRAM exactly once. This single fetch protects the hardware, it allows a 9 billion parameter model to run at the speed of a 3 billion parameter dense model, and remarkably, it achieves 5 to 8 point improvements in math and coding tasks. But how do they actually pull off that single fetch? They use what's basically an extreme data diet, called the 2-bit squeeze. Through a quantization-aware training funnel, they shrink standard 16-bit weights, which take up about 6 gigabytes, all the way down to extreme 2-bit weights, crushing the footprint down to just 0.75 gigabytes. Now, you'd think shrinking data by nearly 8 times would completely wreck the AI's intelligence, right? Well, surprisingly, through targeted adapter training, they didn't just recover the lost quality, they actually bumped up benchmark performance by 1.5%. So let's put this whole blueprint engine together into a clear pipeline. Step 1. Compress the massive model down to 2-bit weights using QAT so it easily fits. Step 2. Store it all in the NAND library and use Mixture of Experts to select only what's needed. Step 3. Fetch it exactly once using IFP so you don't destroy your hardware. It's exactly like knowing the precise paragraph of a specific book you need to read before you ever get up from your desk.
Part 5. Chain reaction in global supply.
Now let's zoom out, because this microarchitecture is causing a massive macro shift. Because NAND is now acting as warm memory, Apple Intelligence requires an immediate 7 GB baseline today just to turn on. But look ahead at the trend force projection. By 2026, flagship smartphones will require 40 to 60 gigabytes purely for AI models and cache. Meaning the 128 gigabyte storage tier? It is officially dead. 256 gigabytes is the new mandatory baseline for the entire industry.
And here is where the math gets wild. When you apply a multiplier to Apple's 240 million annual iPhones, a mere 64 gigabyte increase per device creates a 15.4 exabyte mountain of new NAND demand globally. If that shifts to 128 gigabytes, demand surges past 30 exabytes. A software efficiency trick on a single phone is literally dictating global hardware manufacturing at an unprecedented scale.
And this brings us to a universal shift happening across the entire computing landscape right now. Whether we're looking at Apple at the edge, SK Hynix in the data center creating high-bandwidth flash, or Samsung placing advanced NAND directly adjacent to AI accelerators, that strict, rigid boundary between cold storage and warm memory is collapsing entirely. NAND is no longer just a passive commodity where you drop your photos and forget them. It is a vital, active participant in real-time AI inference. Architecture is greater than raw capacity. That right there is a whole game. Apple completely sidestepped a potentially catastrophic DRAM pricing crisis, not by opening their wallet and buying more hardware, but by fundamentally rewiring how their silicon interacts with storage. Software routing logic has literally become their ultimate competitive moat. Which leaves us with this final thought as we wrap up today's explainer. As these models continue to grow infinitely larger, true edge intelligence is going to require seamless collaboration between the desk and the library. So ask yourself, in the explosive era of on-device AI, is hardware supremacy defined by how much physical memory you have, or by the software logic that dictates exactly how fast you can retrieve it? Keep exploring, and we'll see you in the next one.